Hello everyone, welcome to ECE350 electromagnetic fields. This course deals with electrical and magnetic properties of materials as well as wave propagations, right? So the goal for this videos lecture is that we will try to uh, discuss theoretical background in the video lectures. Then when you come to the class, we try to solve problems to make sure that you understand the theory and you know how to apply that to solve problem. So I'm trying to get the theory out of my way in the video lectures. Then when you come to class, we're going to spend most of our time in the class to solve the problem. So the chapter one. Chapter one deals with waves and phasors. Today we're gonna talk about waves, and next two classes we're gonna talk about phasors. So again, introduction, electric and magnetic fields, wave, traveling waves. That's the key point here. I'm gonna spend most of our time on this one here, most of the time on this topic here, and all other introduction you can review on your own time. So as an example, E&M fields, applications everywhere around you, from satellite to electric machine to your iPhone or any smartphone, optical fiber communications, and any sensor you use around anything that also electromagnetic property and applications. So each application is wide, and almost every aspect of our life has some kind of electromagnetic field applications. I'm going to spend time over here. These are just units. And over the years, almost over the few centuries, electromagnetic fields evolves from a very basic theory of Ohm's law over here to Maxwell equations, and also Faraday's law, Ampere's law, Gauss's law, and Nikola Tesla, who invented AC current and AC motors. Then your X-ray, to Albert Einstein, who got the Nobel Prize for photoelectric effect, then goes into your first telecommunications, first televisions, first IC, and so on. So at the end, you end up with smart devices now. So it's like sensory after sensory. Scientists and engineers devoted their life to develop new technology. That's why we have now all kinds of smart technology around us. And also fundamental forces, nuclear forces is the like subatomic forces, which nuclear force is the strongest, also in subatomic levels, and gravitational force is the weakest, but is the very big microscopic systems, right? So you learn this gravitational force equation in your physics 160. I'm not going to spend time on that. That is the equation for gravitational force. We're not going to spend any time on this because it's not the focus of E&M field. But as coulombs and electrons, we learned about them in as early as ECE100. So, electrical forces. Physics 260, you learned about this in physics 260, right? What is the electric force between two charges, right? Same equation again here. And also you learned about electric field. If you have a charge, what is the electric field around that charge? Also learned in your physics 260. If you forgot it, I would say go review your notes in physics 260. So see what is the forces between charges and what is the electric field due to a charge. And also electric field due to a charge could be affected by the permittivity. So that's is here. This is the permittivity. Permittivity of a materials is epsilon 0 and epsilon r. Epsilon r is the relative permittivity. Right, and epsilon 0 is the permittivity of the free space. So epsilon 0 is the permittivity of the free space, and this is the permittivity of the media. So right now, this is the epsilon is the permittivity of the dielectric media. And also you learned it in physics 260, magnetic field, right? So magnetic field around a current carrying conductor, B over here is magnetic flux density. B is magnetic flux density. right? So it depends on two things, depends on permeability as well as current and also distance, right? So permeability of free space is this one here. Permeability of any other media would be the same equation. You just saw it in the previous slide. So, and also you learned them in physics. So I would say go and basically refresh your knowledge on magnetic field from physics 260. So there are a few things over here. For static electric fields, your charge is not changing. For static magnetic field, your current is not changing. So E is the intensity, electric field intensity, is volt or meter, and D is the electric flux density, is coulomb per meter square. And this is the equation relates them both. And again, B is the magnetic flux density, and H is the magnetic field intensity, and this is the equation. Put them together. All right. So we're not going to review this because you have learned them in physics 260. We're going to start over here for the E&M field, time varying field. Before that, we're going to cover chapter 1, 2, 3. Then we're going to go to chapter 6 to cover this. And from there, we're going to go 7 and 8. All right. So again, these are the units. You all know that. If you forgot them, there your book has them already in the back page of the book. So traveling waves. When a wave goes through a media, it carry energy, and wave also has velocity. That's why it travels. And we're gonna mainly study waves are linear waves or planar waves. Those are the waves that doesn't interfere with other waves. They just go through that. And transient waves, when you have a sudden disturbance called transient wave. Continuous periodic waves, if there's no disturbance, is repeating the pattern every time, right? So there are the different forms of waves, like circular waves is kind of very similar to your water wave in a pond. Then your plane waveform, cylindrical waveform, and spherical waveform. We're gonna, when I go to waveform in chapter 7, we're gonna concentrate on plane waveform. So sinusoidal waves in lossless media. What is lossless? Means that your wave is not attenuating over time. So magnitude of the waves, like A, is same everywhere in the media. So that means it's not attenuating. That's the lossless media, right? So over here, your Y over here, Y is the height of the water surface. Like say, think of the water waves, is water surface, and this is the magnitude, and X is distance, right? So your wave, this wave can be expressed in terms of time and also distance. Over here, we're taking a snapshot at time equal to 0, and you can see the distance between two peak or two valleys, the same distance. And if you take another snapshot at x equal to 0, you can see the time between two valley or two peak over here. It would be same thing. Right here would be same thing. So that's also would be lambda. This is also t. So if you see over here that you're to travel this distance over here, you need the time t, capital T, right? So that means your velocity would be, we call it up, phase velocity. It would be your lambda over t, right? Travel distance by time, right? This is you can get it from here, but we can also do it by using what do you call it? Some mathematical expression. And what is the phi 0 over here? This is the reference angle. For these two waves over here, reference angle, this phi 0 is 0. For both wave over here, your phi 0 is 0 because starting from the 0 angle. All right. All right. So now, if you look at a wave, this one over here, right, with a constant magnitude, amplitude A. So if you look at like different time, if you look at time equal to 0 over here, you get this one. If you look at time equal to t over 4, is this one here shifted by some distance, and if you look at time t over 2 is shifted by some other distance, right? So now that's how your wave travels through the media. So now, if you rearrange this equation, you want to get this expression over here, you will get cosine inverse y0 over a. Now, if you try to take the derivative of this equation with respect to t, right? So this is with respect to is 2 pi over t over here, capital T, and this one is 2 pi over lambda dx over dt, and this constant should be 0, right? So now if you look at this one here, this is your wave velocity. If you look at that one here, that will come down to same equation we just did in the last slide, right? So this is the wave velocity, meter per second. All right. So now, the frequency is 1 over t. T is the period, right? Frequency is 1 over t. And if you modify that, your wave velocity is lambda f. F is the frequency. So, for example, if you have a wave with 60 hertz, right, is f, and your lambda is, say, 5,000 kilometer, right? Then your mu p would be 5,000 times 3 meter times 60 hertz. So you'll get 5,000 times 1,000 times 60. You will get 3 times 10 over 8 meter per second. This is basically also speed of light, right? Okay, so and again, so your omega, the omega is 2 pi f, so we can express this one as omega, and your phase constant is 2 pi by lambda. That's your phase constant. So phase constant is basically saying that when wave travels, how much phase is shifting from the as you goes through the media. So it's radian per meter. Okay, so how much phase is shifted per unit distance. If you have this equation over here, you can see that there are coefficient of t and beta, or t and x, both are opposite sign. That means that wave is going in positive x direction. If the coefficient of t and x have the same sign, that does mean going opposite direction or negative x direction. So that's how you determine which way is your wave is traveling. And when a wave goes, different wave goes through the media, they're not all traveling at the same time frame, right? So, for example, if at t equal to 0, if this wave has an angle 0 with the t equal to 0, then other two waves at the same time reference doesn't have the same angle, right? So this one over here is coming. If you look at here, this one is coming a little bit after the reference one, and this one is coming before the reference one, right? So that means this one is lagging, this one is leading, right? So that means this is leading, and this one is lagging, right? So red one is lagging. So red one is leading by 45 degree, and green one is lagging by 45 degree with reference to the blue one. Blue one is the reference because that's what it is starting at angle 0 at t equal to 0. So that's why you know which one is lagging, which one is leading. So we're going to stop here for today, and we're going to get to the next lecture tomorrow. So review your materials from the book and come to class to solve some problems.